Okay, so good morning, everybody, and welcome to the tech track. Looks like there's a kind of evil guy who tries to annoy us, but I think, as you already noticed, we are trying to implement some kind of countermeasures, and finally, our technicians made it possible that also Beamer is working, and we have something to present. Very warm welcome to Philippe Thorwen. He's one of our first speakers in the tech track. Philippe is working for Quark Labs and is the kind of specialist and expert if it comes to every kind of technology that tries to transmit something. And of course, he's also an expert for white box crypto analysis. And his talk, Hiding Your White Box Designs is Not Enough, is about a new approach about accessing white box implementations and their corresponding security. So, Philippe, thank you for being here, and please go ahead.
Yeah, thanks for the introduction. That's not true at all that I'm an expert in white box, and I will show you that I don't understand most of them, but it doesn't really matter if you want to attack them. So, thanks for the introduction. So, indeed, I'm working since very soon at Quark Labs. Just a few words on myself. I love free software, security, of course, playing CTFs, and photographies. Just a note, what I'm presenting here is from my previous job, actually. So that's why you will get the slides with this NXP logo on it, because this is research work that was started there. But now it's a bit also out of the box, and there are more people involved in it than just NXP people, hopefully. So very briefly, the agenda for today, it's first I will explain what is white box crypto, because maybe you're not all aware of what it is. Then I will explain very shortly also what are software execution traces. Probably also most of you know already about that, but it's a tool that we will use then to do the attack. And this attack, we called it this differential commutation analysis, and that term sounds a bit academic, will be explained later. So first, to explain white box, maybe we need to step back a little bit and remember why we are talking about white box. And first, it started all with black box. And that's traditional crypto setup where you have Alice that wants to communicate with Bob, and cryptographs are making some safe protocols. And here, for example, you have some Diffie-Hellman, and you suppose that if you have an attacker that is only passive and look at the messages, that should be pretty safe. And that's how crypto academia works, and for years it looks like okay, and then sometimes you may have some surprises and new results that show that a very powerful attacker like the NSA is quite likely to break actually a lot of these Diffie-Hellman in the wild. By the way, if you didn't recognize this face, those ones, I don't have to present them, but he's Mike Rogers, and he's the director of the NSA, and I promise it was not photoshopped. And neither the hands, he was very like, ah. Okay, that's a black box model, which means the endpoints are not taken at all in consideration in the attack model. It's just black box. It's communicating, and you just can observe this input and output. But in real life, you don't have black boxes, you have real physical objects. And this is the same card here, for example, for these troopers. So in the gray box model, this object is interacting with this environment with just more than this input and this output. So actually, if you put it, for example, in a reader, and you take care of what is the power consumption of that card, and you take a very careful measurements on it and send that to some PC to make some cryptanalysis, you may find the key which is used within this physical object. And in that gray box model, there are many different attacks. You can have also electromagnetic side channel, so you don't measure the power directly, but you measure the radio that come out of that chip. By the way, this is the Chip Whisperer, which is a nice open source project if you want to try this kind of stuff by yourself. And you have different kind of side channel attacks. Sometimes it's SPA, a single trace is enough to break the key. You can also be more invasive in the way you attack. You can make glitches on the clock, for example, and see what happens if the chip behaves badly. You can do laser attacks. where just beaming some photons on this electronic will introduce some currents and will have a logical effect. Or you can be really, really invasive and decaping the chip and probing with needles directly on the wires of the transistor. So why am I talking all these details while we are talking about white box? We will come to that later because we will use also these for the white box actually. The white box model is different. White box, what do you have? You don't have this physical object anymore. Actually, you have just your code, just the executable code. And that code will be executed in a hostile environment, which means you have no control where it will be executed. And of course, to have this kind of all these, you need the corresponding laptop. And you can do static analysis, dynamic analysis, and of course, you can do whatever you want. You can observe the data, you can observe the code, you can change it, you can change the instructions, you can change the values in the registers, in the memory. Well, basically, you can do whatever you want. So the white box model is a very, very powerful attacker model. And if you want to design something secure in that model, that's really, really difficult. So the only line of defense is your implementation, actually. You have nothing else. You cannot rely on some hardware or whatever. And the usual tricks is code obfuscation, integrity checks, anti-debug checks, and this kind of stuff. So just two examples to illustrate. That's a funny one because someone found that the move instruction is actually true incomplete, so why not just writing a problem just using the move instructions? And indeed, it's a bit intimidating if you're reverse engineering and you're finding this kind of code, so what is going on there? Another way, classical one, is code flattening. So instead of having a graph of the different basic blocks in your code, you get all your basic blocks aligned on a single line and some glue logic that tell you from which one you go to the next one. And if you want to attack this statically, yeah, okay, that's pretty hard to do actually. Statically, dynamically, that's another story. So now in that model, if you want to do cryptography, what happens? Well, first, why do you want to do cryptography in the white box model, which is so powerful? Two use cases that are quite classical. The first one historically is the DRM scheme, because there, well, you want to run your code on the criminal's machine, the user's machines, and that's very well known. But recently there was another use case that is becoming more and more popular, which is this mobile payment and what is called host card emulation. And there, the user is not the attacker anymore, but it's more like financial malware that will try to steal your money that could be on your phone. And host card emulation, what is this briefly? You have two modes to do payment on the phone. One is using a secure element, which is actually like your banking card embedded in the phone. And the application processor doesn't see anything about that. And the HCE is, well, let's get rid of that one, and let's do everything in software. So you can just download an app, and you basically just download your credit card and use it like that. So, of course, for criminals, that looks like a promising target here. Much easier to observe and interact with than with like a banking card hook in your phone. So when you do crypto and you want to protect it, well, actually, code obfuscation and all this kind of trick, that doesn't really apply very well. Because code obfuscation is about hiding the algorithm that you want to do. You don't want the attacker to know what you're doing. But in crypto, well, this is standard block cipher. So as a reverser, I know what the code is supposed to do. The only thing I don't know is the key, and I want the key. But the key is not code, it's just data. So most of the code obfuscation techniques, they won't help hiding the data. And for example, there was this very old attack by Shamir on RSA. It doesn't care about the code, it just look at the memory snapshot, and well, where there are random bits somewhere in the memory, that's probably where your key is, because the rest contains some structure, just having a look to the memory wrap. you can have a pretty good guess where your keys may be. So you have to find other tricks if you want to do crypto in the white box model. And it all started in 2002 with the first paper by Cho, which is pretty well known in the white box cryptography academia. And there say, well, there is one way to do a super secure white box. It's just do everything in one single table. You give a plain text, send it to your lookup table, and the lookup table will give you the corresponding ciphertext. That's super secure, but how large is this table? Well, you cannot really afford that. So practical white box on IIS, for example, here, you have to break down this cipher into smaller lookup tables that are interlinked between. Already at that stage, he thought, okay, but these intermediate values that are sent between the different tables, that could be observed, and they need to be masked. Otherwise, it would be a bit too easy to observe like some plain intermediate values of your different rounds. So he's encoding these values, which means that in between each of the table, the output actually is encoded with a random table, and the input of the next table is decoding this intermediate encoding. So if you observe what happens, whatever here or there, it's not the plain value. It's a value which is masked with a randomly generated table. Sometimes you have things that are still quite big tables, because here you have 32 bits times 32 bits in entrance. And so you have to break down this kind of big table into a network of very small XOR tables here, which are actually just 4 bits wide. And then the rest of the story about the academic white box research is this was broken. Someone else proposed something else to fix and to resist the attack that was published, and then another attack was published that broke that scheme, and so forth. And today, I have to recognize that all the academic white box schemes that were proposed, they're all broken on paper. Now, the industry still is using it for DRM, for HCE, so how comes that? Well, first, they stop publishing their design. They don't tell you anymore how they do that. Otherwise, some academics will do the math and maybe break it again. And so just hide it, some security by obscurity there. And on top of it, once you do your binary, also add some classical code obfuscation techniques. It will just also slow down the work of a reverser that want to break these kind of things. And sometimes you have some bold claims that say, yeah, we have HCE that now it's as secure as what you could do with this secure element. And you have rarely publications that claim that they could break really industrial white box design. So there the status is a bit unknown there. There is no academic publication for that. But why do I keep saying academic? Because if you want to apply really an academic attack, what does it mean when it's on a real product? First, you have to reverse engineer all this code obfuscation layer to discover what is the white box layout below. And once you have this white box, you have to have some knowledge about the design which is behind the choice of these tables, for example, if it's a table lookup white box. And then you have to apply this academic attack. And academic attack, they look like this. You have the references over there, and well, I don't know for you, but that's why I say I'm not an expert in white box, because for me it's all Chinese. I just can't understand. I can read code, I can't read that. Or I really need a lot of concentration, and I don't go much far. So when I was busy with this kind of problem, I thought, okay, I have to find another way, because the maths way, that's no way for me. So is there a way that we can find our keys without too much effort, indirectly, also in terms of reverse engineering? And that's where we will come with this attack. The attack is using a well-known technique where you are in this white box model, is that you can do software execution traces. What does it mean? It's just that when you execute the binary, you record everything. Every single instruction going on, every single data that goes forth and back to memory, optionally also even the register content. I mean, you record as much information as you can. And we used in the various white box simulation, we had different techniques. So we used dynamic binary instrumentation using Intel pin, Valgrind. Why both is actually we started with Intel pin and then, oh, there is no support for ARM, so we have to find something else. So we went for Valgrind, and we wrote plugins for both to be able to do the traces that we wanted. In some situations, don't use just this low-level binary instrumentation, because if you're playing with Java code or Python code, it's becoming mental. It's much easier to hook somewhere in the VM there. And for some situation when you have very exotic chips you run in an emulator, there it's very easy actually. You just change one line in the code source of the emulator to say, okay, whenever you read something, just dump it somewhere in the file and you're done. Once you acquire this information, this trace, what do you do with that? Again, I don't like to look at bytecodes and things like that. I like to have more helicopter view. So actually, I started using visualization of the traces. And here, it's a bit like Back to the Future. Actually, I got inspired by a presentation made by someone from Quarks Lab 3 years ago. And they presented a tool that do software traces, which was called Petra. But unfortunately, it's not open source. So I said, OK, let's do it again. Internally, let's develop this kind of tool. But I reused completely the same conventions because I found them quite nice, even if there may be some unnatural. Because actually, the time starts here and then goes down over there. So it's a bit like a waterfall for those who are doing software-defined radio. Maybe it speaks a bit to them. Then on the other axis, you have just the memory address range. And we have some color conventions. So the black is some instructions. The green is data which is being read, and the red color is for data being written. And here in this example, we are on an exotic CPU actually, and the stack is somewhere between the code and the data, which is a bit unusual for if you look at Intel or ARM, for example. So what can we do with this kind of visualization where there is no even instruction visible directly, just dots? Well, first, when you have a big binary and you execute it, you want to know where is the crypto. And here, just looking at the patterns and the loops, for example, you get this part here. And you can recognize 9 times like 4 lines, and sometimes it's a bit longer. So actually, you have 9 times 4 blocks, and then a 10th one a little bit different. Any guess what kind of crypto it could be there? What crypto cipher is it? So we have actually 9 plus 1, 10 rounds. IS 138. No, doesn't speak to you. Sometimes it's not possible to guess where the crypto is because all the code was completely linearized. So there is no jump at all here. But if you look to the data access, then again, you can see some patterns coming on there. And here we've like 15 access to some tables and a little one there, so 16. So something with 16 rounds, a good chance that it's actually a DES algorithm. So just looking at that, I can already see where and what kind of crypto is going on there. Sometimes it's also not really possible observing the data reads. Maybe if I zoom, I can see some little things, but it's not easy. Then usually what I do is just looking at the stack, because on the stack it's really hard to hide whatever. Sorry, I forgot. either it's serialized or it's completely looks like randomized access on a very large table. And you see the dots here, so there also you don't see structure. So you look at the stack, actually. And in the stack, again, you can see very easily the structures. So here we have, again, like this. That one, we have an IS again. And so why 9, by the way? It's because you have 10 rounds in IS, but the 10th, the last round, is a little bit different. There is one missing operation. That's why you don't have this step there, but you have something slightly shorter and different. And here on this version, you can see indeed that there are 10 such operations and 9 others. So this is a full round, and the last round is just this little one where you're missing the counterpart over there. So all these pictures are from stacks from very different architectures of very different white box implementations, but they all speak by themselves, even if they are very different, with a very different look. You can always see what you want to see there. Yet another one. So, okay, that's nice, but still I want the key, just not to know where the stuff is going on. So we need something else. We need the attack. But the visualization is helpful because on very small examples, I can do the attack without knowing anything and attacking the full binary. Now, on a real larger application, the attack works as well, but it's much slower if I'm looking at data that has nothing to do. So it's better if I can reduce my scope and look where is my crypto. So I know for the next attack, I will just look at the data that's going there, and I don't care about the rest of the data going the rest of the program. Otherwise, I will get gigantic traces over there. So that attack, I will go back. You remember what I said at the beginning, gray box model. We can measure power traces. And there in the gray box model, I don't care about the actual hardware implementation of the crypto. There are attacks that just work, unless there are specific protections on the chip. But at the very beginning, with this when this attack was presented, and it was already in '98, there was no protection, of course, against this kind of stuff, specifically in the chip, and all the chips could be broken with the same method. So there, how does it work? It's about a probable correlation between the power consumption of the chip and the content of the data that are used during the computation of the cipher. And it's using what we call Hamming-Weiss model. So why Hamming-Weiss? It's because if you look, for example, here just an adder in hardware, so you're just adding 1 byte within 1 byte and you get 1 byte out. The output, if it's like 101001, that means there will be high voltage here, low voltage, high, low, 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 high, etc. So what makes power consumption on the silicon? It's actually transistor switching. So depending on the output value, you will switch some of the output high and the other stay low. So the observable power consumption of the chip is actually the sum of the effects here. So we'll consider the Hamming-Weiss of this, which are 1, 2, 3. There are 3 bits high, which means there is a Hamming-Weiss equal to 3 for this one. And then what do? You record many traces with different inputs. So you're encrypting or decrypting many plain text or input text. And you can observe already with a single trace, for example, here, and there you have the time on this axis, and on the other axis, this is the power consumption, so here the voltage that you can find on your resistor. On the previous slide, so here we introduce a little resistor, and we measure actually the voltage drop of the resistor, which gives you a good idea of what is the power consumption behind. And then comes the crypto part. I mean, okay, you recorded some stuff that depends on some intermediate value. How can you get a key out of this kind of information? Well, look, for example, at the very beginning of the IS encryption. The very first round, it's taking each byte of your plaintext, which are over there, and it's mixing, XORing it with 1 byte of the key, of the first round key, which happens to be the IS key in the case of the IS scaling. And then you get the result, which is just XOR, and this result, you go to a little lookup table, which is called a SBox, and it gives you another value. So now, what happens if you make an hypothesis on the value of the key, because you don't know that one. So you don't have to guess the full key, you just guess 1 byte of the key. And you say, well, if my byte is equal to 0, then when I XOR it with this plaintext, I will get that value, and I go to the SBox, and I go to that value. So my only unknown in my equation is the byte of that key. And I can do that for many different traces, for many different inputs, and many different values over there. It will give me always a supposition about the value of the target over there. And if I look to that value bit per bit, I take 1 bit and say, OK, if my bit is equal to 0, according to my hypothesis, I will take the trace and I put it here. If I get a 1, I will take my trace and put it there. You do that for all your traces. You make an average of them, and then you make the difference between your 2 buckets. And you see, is there any difference statistically in the power consumption between that set and that set? If the key guess is wrong, you have sorted your traces completely randomly. So statistically, there should not be any difference between the 2 sets. If your key byte is right, and if there is this correlation between the power and what's happened in the chip, you will get a peak. You will get something like that. So on average, you see just noise. And when there is a significant difference between your 2 data sets, you know your key byte guess was right. And just keep doing it for all the key bytes. And at the end, you just broke indeed the key. So it's a very powerful attack. And you don't need much. You need access to the input or the output, because you can attack the beginning or the end. It doesn't matter really to have both. It's nice to have both, because when you guess a key, you can just check the key and see if it matches or not. But it's not really required to have both input and output to mount the attack per se. You have to have a mean to observe the power consumption or some other side channel like the electromagnetic emanation from the chip. And of course, there must be some correlation, what we call some leakage between what you observe and what is really done in the cipher, in the block cipher. So the differential computation analysis, what do we do? Well, we can port the white box to a smart card and attack the smart card with these hardware tools. Wow, we can do much better, actually. Yeah? We can use our software execution traces, take the data, somehow make something that looks like a bit a power trace, and use the standard tools that are made to break hardware acquired power trace. So one way, for example, if you trace just the 8-bit data reads, so you have just 1 byte that is read from the memory, put just them side by side, and you get something that looks like a bit a power trace. And if the white box is quite weak, you may already break it. That could be possible. But actually, building the trace that way is wrong, because the high peaks, the high differences are due actually to the MSB of your byte, just the strongest bit of the byte. But the least significant bit has almost no effect on the trace, so it's just lost information. So maybe it's better to build it with this Hamming Wave model, where all bits have an equal importance in the result. And then you get a trace which is actually with only 8 possible values, because Hamming Wave is about how many bits are equal to 1. So it's between 0 and 8. This kind of trace, you can already break some white box crypto, but we are still not using all the information available because actually Hamming-Wave was a model for the hardware because we didn't know about the exact bits that were activated. We were just modeling to say we observe all of them at the same time. But here, we know each of the bits separately. So a much better way is actually just to serialize all the bits that we observe. And then you get a trace that looks quite strange. If you're a bit used to hardware side channel and you see these power traces and say, yeah, I have my traces too, and I want to use your tool to break it. That's not a power trace. What is it? It's just 0 or 1. That's the only value you get in your trace. But actually, it looks really great, and if you want to get back to an analogy with the hardware model, it's more like this one. It's not about sniffing the power consumption. It's about really having needles that go to your bus, that go, for example, from the CPU to the memory, and you can observe each line of your memory bus very precisely without any noise, without any measurement error. You just get directly the real values. So then what do? You feed it to this usual DPA tool, so the tools that are made to do the differential power analysis attack that I explained before. And internally, we used some proprietary tool, pretty expensive, but well, I was working for a chip designer, so we were using this kind of stuff. If you're on, with the Chip Whisperer, there is also some open source software that is able to do this kind of attack, but it was done obviously for hardware, not for white box, not for attacking these bits. So today it's only the Hamming-Wave which is implemented. But you may extend the tool to have a better support, for example, for these white boxes. And academia, well, they still love playing with things like MATLAB. And I will talk about that at the very end of the presentation, but with a little new one, just for troopers. So little tricks and tips if you want to try it by yourself. What kind of information do you need to trace to make this attack possible? I like really looking at the stack writes because it's less information than the recording, for example, all the data reads. You don't need to look to the stack reads because whatever you read from the stack, you wrote it somewhere before. And it works pretty well for almost all the white box I looked at. But sometimes it doesn't work like that, and you have to look to something else because maybe the leak was in the register value and not written back to the memory. So look at the data read can be interesting. Usually then I only look at byte data read because white boxes are table-based and they are table-based with byte and not longer words. You may also look to the address of the data which is being read. And the address is very large. But again, it's about small tables here and there. So if you take just the last byte of the address, it may be also enough to have a leak and information. And if all this doesn't work, you may also look directly to the register content. But tracing register is very slow, and I never needed actually to do it. Then you need also to, of course, acquire the plaintext and of the input or the output. In the little examples I'll show later, it was obvious, but in a bigger application, it might be that you don't have a direct access to that information, and then you need to do some also dynamic binary instrumentation to hook somewhere and get that information out. A little trick when you deal with quite large white boxes is try to reduce the size of your traces. So then you go back to this visualization tool to see, okay, I want just to attack the first round or the last round. So I don't even have to trace all the full cipher operations. I know my first round is over there, which match with this range of addresses. So let's trace only what happens in this range of the code. And sometimes, for the obfuscator, is doing a hell of mobs everywhere, but most of them are not related with the crypto. It's just about hiding the instruction being executed. So if you make several traces, you will get always the same value there. So just do some basic statistic to get rid of all the fixed value in your trace, and you can really compress your trace pretty well. Some examples, obviously I present here only public white box challenges, nothing from a vendor. The very first one who published really a challenge, and not just academic paper, but a real binary, was Breakwiser in 2007. It was a DES implementation, so what you saw before, and this one, it was this challenge actually. So it's a show plus some things that it didn't really describe. And there, I had already my tool suite when I was looking for that one actually. And the hardest part was to find a binary because he was removed from his website, and it took me quite a lot of time. But once I got the binary, it just took me 1 hour to make the glue code, to acquire the traces, and break the key. That was really, really fast to do. Another one is the HackLU 2009. This one was a crack me for CTF, and it was a Windows executable. Clearly, Intel Pin Tool can work on Windows, but I'm not really a Windows guy, and I was lazy, so let's try to trace it just under Linux. And just using Wine and Linux and a tool to automate the input acquisition. I needed only actually 16 traces, so I could have done it completely manually, but here I made it automatic. Here again, just a very few traces were enough to break it. And actually, when you go as down as like 16 traces, it really means that actually there was no intermediate encoding in between the tables. Otherwise, still you need some more traces than that. But okay, that's fine. I mean, it was for a short CTF that lasts for 2 days, so it was not meant to be unbreakable, of course. Huh? Another one is the SSTick challenge. I mentioned it because here that was in Python, and you got actually a Marshall object that contains white box stuff, and I even don't know yet today what is really the structure of this white box behind. So as I said before, don't try like pin on Python. I tried just on Hello World, no crypto, just Hello World, and it gave me like 6 terabytes of traces, and I said, okay, stop. So in this case, you may instrument the virtual machine of the interpreter of Python. Here, actually, it was even easier because there was a little external class, external to the object, which was this bits helper class. So I just instrumented the class to say, okay, whenever you create a new object bits, just show me what you do and give me the data. And again, 16 trace, again, no encoding. So we looked for the strongest publicly available white box, and that was the Karumi. Karumi is the latest attempt in the academia to fix the show design. And there are stuff I don't really understand, so it's talking about dual cipher, and so there are some isomorphism between representation of your AES here, whatever. By chance, because it's again a paper, and that's a very big disadvantage of my attack, I can't break papers. I need binary. I need the real stuff. So hopefully someone did a thesis and broke Karumi, but he was kind enough to put some source code with a Karumi implementation. So we used the implementation to do our own little challenge, and we broke our own challenge. And here you see, okay, it looks like it was better. You need still quite a lot of traces to break it. Well, a lot if you compare to hardware. Usually a robust hardware, you talk about millions of traces. So here there is still some scale in between this hardware and software. And, well, yeah, we look, of closely. So property stuff, I can just give you the range of traces needed to break those schemes. It's like between 200 and 2,500. And we try that on DES and AES, and it works pretty well. But, yeah, sorry, can't speak too much about that. So we are doing the same as for we attack a hardware, but here there is a big advantage as a designer of a white box to be attacked by that model and to work hand to hand with the hacker who tries to break your stuff. Because here, we can go back to the design. Once we broke the key, or we just know the key, I tell her the key, we can do a known-key analysis. And this is a special kind of trace where you can see really at which moment it starts leaking information. But you know how you constructed that information. So you know exactly what is the corresponding instruction in the binary that created that leak. And of course, if you work hand-to-hand with a designer, you can work on a debug symbol version of your binary, so you can really tell him, look in your source code at that line, that's at this point that my attack is working. And that's something you cannot do usually with hardware. Hardware, when external lab is evaluating your chip, you say, okay, broke your key, how did you do? Well, there is some leakage at that point, but then you're back to your chip design and say, okay, where was it exactly, that leak? And that's really tough to understand sometimes what is the cause of the leak and how to fix it. And by the way, this is not white box crypto. This is just code obfuscation, but for the fun, I also tried this Mobfuscator, right, that converts a program into MOFs. And I did that on a single standard AES implementation. When you look at the trace, it's pretty impressive because that's a regular AES. Actually here, just the first 3 rounds, otherwise this one is really too big to be displayed on my program. And then here you don't see anything anymore, actually. Because this black one is just instructions. Actually, it's a one single, very long loop that goes over and over and over. And it's just like scan lines of the screen. It's just fill the screen entirely. And you have here many memory reads, of course, because a MOV is a memory read or write. And you can still distinguish somehow here something that would make correspond to that, but okay, it's very hard at this point to see anything. But if you do these traces with these binary traces, and on a binary trace itself, you hardly see also something like round. But there are other tools like doing autocorrelation on a trace. So autocorrelation, what is it? It's you build a graph where you compare the trace to itself. So it's twice the trace, here and there. And if there is a portion of the trace that look a little bit alike another one, then you will have some white stuff there. And here, immediately, you see that indeed there are kind of repetitive patterns that on a single one you could not really see, but here it's really clear. And you can see the 10 AES rounds like that. And the information, of course, is mirroring. What you have here is the same as what you have there. So I use also this little statistic trick to compress these traces and get rid of all the information that was just stable across all the traces. And here, actually, the leakage occurred at that point, where, if you remember how the AES work, when the mix with the key was occurring. So usually in a white box, the mix with the key is hidden with this operation in one larger operation, and the leak occurs somewhere more like here. But because in this case it was not white box, it was just directly mixing the key, the leak is just occurring a little bit before. And if you're curious, there is some write-up of that on my wiki. So it's magic, but can it fail? Yeah. I had some cases where the white box was resistant, completely resistant to the attack, no matter how many traces you take. How comes? One example here is the No Such Code Challenge 2013. That's because they use white encoding. You remember in show, I show you the XOR table with very small input, 4-bit input, 4-bit output. Here, we have larger encodings. It's a full byte. And your S-box is here. The mix with the key is here. And this is one single table. So the input and the output are encoded with some other tables that are a bit like similar to the S-box, except that they are completely random. So what you use to attack normally is the S-box information, but it's completely hidden by a random here and a random something similar there. So when you look at the total, there is no linearity, non-linearity of the S-box which is visible anymore. But the problem when you use wider encoding, this table becomes really huge. And in an implementation, just these three tables compared to all the rest are as big as the rest. So there is a trend to reuse this one, so otherwise your binary becomes really too much. And from the moment you're using it, there are other type of attacks. And finally, I mean, this one, I also broke it, and it's also explained there, but it's not using the same attack. And the chess challenge also used kind of the same model. It was on a Game Boy ROM, and it's also one of the picture I showed earlier. So how can you protect against this kind of attack? You can look at what the hardware guys do to protect their chip against differential power analysis. One trick is to use runtime randomness. Have a random generator that provides you masks, and you use your random mask, to mask your intermediate values. And if the randomness is good, on average, when you look at your traces, there is no correlation anymore. It all looks like random. But on the white box model, how do you get your random? That's not that easy. I mean, if I see in the program, yeah, you want a random? Yeah, 0. You want? 0. So that doesn't really work on the white box model. Another trick is to use random delays. So again, random, well, you can use the input of the program as a kind of random information. This is the only one that is reliable in the white box model, actually, because that one, I cannot change it in the program. Otherwise, I'm just changing the input. And so, of course, I'm just fucking up all the rest of the computation. So you may introduce kind of random delays based on the plain text that you are using. But then, again, even if the bit representation looks really hard to align, you can also get out of the traces information about which instruction is getting executed. And if you get some random in your program, that means that you have some loops at some points, and sometimes you're looping a bit, sometimes looping a bit more. So if you look really at the instruction trace, you see that. So you can use that information to realign the traces that contain the data information. So that doesn't work very well neither. So it's pretty hard, actually, to build proper white box technology today. Of course, we are not talking about absolute security, but the game here actually is just to get with a good enough security. If it costs too much to the attacker to get your key, it's not worth. If it's DRM for a football match, he won't spend a week to scramble the match of the evening. I mean, it's already, information is not valid anymore. But when we are talking about HC and money and things like that, it's a bit different. And here with this kind of cheap attack where you saw that in very basic cases, just 1 hour just to discover and build the very first attack. And that means the next attack just takes seconds, just once you have your setup, of course. If it's a white box with another key with the same framework, you just put it in your automatic tool and it's got automatically broken. So the equation is still valid here, just that now the cost of the attack got quite cheap compared to the previous academic attack where you have to do all these maths to find something. So we made kind of a bridge between the white box model and the gray box model. Say, okay, white box, guys, it's great to work with all your equations, but don't forget we have all these attacks that work in the gray box model, and you're supposed to be robust also against those one, not only on the math one. And when there is an attack that works in the gray box model, it means with some effort you may probably describe the same attack mathematically. But we don't care about really the maths here. We just try and it just works. Why does it work? It works. That's fine. Unless you want to write a nice paper, you will try to understand why and write all the equations that prove that it works. I don't need a proof. The proof is my POC. And what do we have else on the gray box model? We have also some other, that was the very first basic attack, this DPA. It was from 98. But we have also higher order DPA, which means correlating not just one single position in your trace, but correlating several information all together. With CPA, which is with some other statistic model. With DFA, which is fault attack, differential fault attack. And on white box, by the way, this one, I'm not covering in the talk, but it works great as well. And there, actually, you're injecting a fault in, for example, somewhere before the last round of your IS, and you just observe the ciphertext that got corrupted. And just getting a few corrupted ciphertext, you don't know what you did as a fault. You don't care about what you did exactly. But just the fact that there was a fault, and you compare your fault with the correct one, and you get a few traces like that, you can also break the key pretty easily. That works then well as well. And here, all the game was about breaking the key. But in real life, when you deploy white box, getting the key is not the only possible attack. You can also just maybe lift the code with the white box. You don't know the key, but you can still reuse the library with the white box, and you can still decrypt whatever you want to decrypt. You don't care about the key. You have just a bit of code that does the job for you. And there are also attacks inverting the function, because all these lookup tables, you don't know exactly what they do, but you can still reverse all the steps. So given one output, you can see what was the corresponding input, which means if you have a white box encryption, you can make a white box decryption out of it without understanding the little gory detail of the design. So making some resistant white box crypto in this white box model, that's pretty hard. So what I showed is almost the end of the presentation, but maybe it's just not the end of the story. Here, just the beginning of the story. And some troopers announcement here. We released all the code 2 weeks ago with the first tutorial that was posted on the blog of Incinerator, actually. So here, yeah, sorry, again, some superhero. That's to identify a bit the different pieces that we released. There is Tracer. It's a super villain, actually, but it has a nice name. So we have behind that Tracer grind, Tracer pin, which are the tracers based of Intel pin and based on Valgrind, and the visualizator, which is Trace Graph, which is the tool I use to show all these pictures you saw before. That part has nothing to do with white box. I mean, it can be very also useful just for reverse engineering, some code obfuscation, just to see how things are going on, to have a more like a helicopter view of code obfuscation. The second one is Deadpool, because you know in the comic, the crazy little voice in his head are with these white boxes. And anyway, it's also from a program where people were wondering, okay, who will be next in this pool of experiment to be dead, or something like that. So that's our repository of all the public white boxes we presented. Currently, there are only 2 of them, but we will put more once we get all the framework ready for all the attacks. But here we've already Wither and HackILU in it, for example, and with the script to attack them. And this Daredevil I mentioned before, that's the tool that does the sidechain analysis, because we realized we were using Rescue tool, which is not open. So if we release something, better to have a full framework release We looked for some open source side channel tool. We didn't find really what we wanted. Hopefully we had some internal one done by a student, so we decided to release it at the same time. And that's not just me, by the way. That's a lot of people behind these tools. And you see it's not just NXP today, but it becomes also from a larger audience. And when we released it like 2 weeks ago, a few days later, a student from Munich working an internship in Frankfurt told me, oh, I'm working on the subject, it looks nice. Look, I did a Docker image for you. So now we've also Orca. If you want to try, you have a Docker image so that you don't have to worry too much about setting everything by yourself. You can just try that. So I'm done, and the paper, the academic, we wrote also academic paper, is available on ePrint, but I'm very proud there is no single formula in the paper. So you can read it, you will understand it, I hope, not like the white box paper I talked about before. Thank you.